Thanks, Anubhab and organizers for this invitation. It's an interesting conference, but due to we are not in Bangalore, so it happens that classes are to be taken and so on. So I'm not able to attend all the talks, but hopefully we'll meet in person in near future. Okay, so this is what I'm going to talk about. I'm presenting old work. It's 2014, 15, 16 in that period. And this work are done by my ex-PhD student, Abhishek. Sadab is presently working on some of the stuff, and Manohar. Okay, so some advertisement. This is the two books I wrote. The first one is relevant for buoyant flows. It has stability stratified and RBC as well. And this review paper discusses with the energy flux, which I'm going to discuss today. Okay. This is another book on energy transfer, like what Thierry was talking about. Of course, I talk for idealized systems, but it has a lot of details about energy flux. Okay, so as I said, I'm going to talk about a very general topic, and we wrote this paper in 2014, and we solved this problem. Okay, let me say this: RBC, there are a lot of talks, a lot of papers saying that Rayleigh-Benard convection has Boolean-Nabokov spectrum 11/5. Some, of course, say it's Kolmogorov, but we conclusively showed that Rayleigh-Benard is not Boolean-Nabokov. In fact, the arguments are very simple, and that is what I'm going to reproduce today. Unfortunately, I still see that in research papers that it's still some people talk about Boolean-Nabokov. So I'm trying hard to say that, okay, that is incorrect. That simply can't work. Okay, so let's look at it. Let's try to reconstruct the argument, which we did some time back. So Rayleigh-Benard convection, we heat from the bottom, and cool from the top. So this part is dense fluid, and the bottom one is less dense. So system is unstable. I mean, the things will fall if so it's unstable. I mean, any small perturbation will just grow. So we know it all very well. But stability stratified turbulence, or even turbulence or non-turbulence, even for ordinary flows, we have low temperature below. So heavy fluid is below, or dense fluid is below. So it is a stable system. If I make any perturbation, it comes back. So we get gravity waves when we ignore the dissipation. But when you put in dissipation, strong forcing, strong nonlinearity, then we'll get a cascade and turbulence. And it is stable in the sense small fluctuation will tend to die out unless we keep forcing it. So this is very well known. I don't need to belabor this point among this audience. But this stable and unstable, these two parts make a major difference. Okay, so on the energy flux or energy transfer. Okay, and it is quite a simple argument which I would like to just emphasize in this talk. So for our investigation, we use the same equation. In fact, this is what is causes a lot of wrong kind of well, basically the arguments has to be slightly precise, because the equations are exactly the same. Okay, only we change the boundary condition, or means heavy fluid on top in RBC, and heavy fluid at the bottom in stability stratified flows, or this stratification, this sign of the dt by dz, or mean density by. So this one is which determines your flow, whether it is stable or unstable. Okay, is precisely the sign, this term, which is the difference. So we, in our code, we use the same code. We just make one of them positive, one of them negative, and we investigated various things. Okay, now, this equation everybody knows, so I don't want to talk more about it. This is the buoyancy term. This is exactly same for both stability stratified and RBC, but this term is changes sign, right? And we assume the Bushnell. We focus in this talk on specific regime, very specific regime where it is approximately isotropic. Here we assume that the nonlinear term U dot grad U is of the order of the buoyancy term, alpha g theta. So we are assuming that fluid number is order 1. Okay, and that's where we can assume isotropy, and our Richardson number is order 1. Okay, so that is the regime we are, and we will keep the Reynolds number reasonably high. So we want the turbulence and we want the flux. So let's look at the dynamics, energetics, in fact. Okay, so in Kolmogorov flow, that's what we'll start with. Kolmogorov theory of turbulence. We force the large scales, right? In Kolmogorov theory, we say that we stir the fluid at large scales, and that initiates a cascade of energy from large scales. This is a Wave number k, right? So, and that goes down to a small scale where it dissipates. So this is the dissipation range. So energy is flowing down. We have, of course, have viscosity, and that's what happens. But in buoyant flows, both Rayleigh-Bénard as well as in stably stratified flows, the forcing is at all scales, right? Because this alpha g theta or rho g, the rho g, this is the forcing. This acts at all scales. There's a density at everywhere. So forcing is acting at all scales. Now the question is it taking energy from the kinetic? It is. I mean, is the forcing taking energy from the velocity field or giving to the velocity field? That's what we need to see, and that will determine how the flux will change. So in Kolmogorov theory, we know that the flux, the pi k, this is what we denote the flux, is constant in the inertial range. This is constant, right? This is flux is constant, but this is not going to be the same because the forcing is all over all wave numbers. Okay, let me just tell you right away that for stably stratified flows, the flux will decrease with wave number, SST. But this is not going to happen for Rayleigh-Bénard. Okay, so let's see the argument. What makes the difference? Flux, will it decrease with wave number or increase with wave number? And that is why I call this variable energy flux. So energy flux is changing with wave number. Okay, so that is changing with wave number, not with time, but we just say, does it change with wave number? How far does it deviate from Kolmogorov theory? Okay, so this is a very dense slide, but time is short, so I'm just going to make it very quick. So Buoyancy theory, that was for stably stratified turbulence, SST, T for turbulence. Huh? And that theory says that it is dimensional analysis essentially. So the kinetic energy gets transferred to the potential energy, and the sign of the energy transfer from kinetic to potential. So energy goes from kinetic, U squared, to potential, which is rho squared. Okay, so theta is temperature fluctuation, but you can also treat it as density. Okay, so the arguments are the same. So this is the term which determines the sign of energy transfer from U to rho. Now we know that it is stable. I mean, the stably stratified turbulence is stable, so energy will flow from kinetic to density. Of course, assuming viscosity is non-zero and there is a cascade. So we can, but the arguments are slightly more subtle, but it's stable. So you can imagine that any fluctuation in U will try to go into density. Will try to transfer to density. Okay. Of course, there's energy cascade of U, but there is a depletion. So the analogy which I can think of is that energy going from central government of India and is going down to village till, I mean, cascades, state, central to state to district to village, but in between there is corruption. So energy which reaches at the bottom level, it is less than what is supplied. Okay, so that's a good analogy. So the flux is decreasing with wave number. This is a flux. Okay, this is a flux. It decreasing with wave number, and in fact, it was shown by Buoyancy Term in the same paper in 1959 that this flux will decrease with wave number k minus 4/5. Okay. Now this is for stably stratified turbulence. Now, what is it for Rayleigh-Bénard? Rayleigh-Bénard convection. What is the sign of this term? Now, it just occurred to me while teaching in a class. This sign cannot be negative. Why? Because in a Rayleigh-Bénard convection, when we heat the fluid, then velocity increases, right? I mean, the flow, the thermal roles become more and more prominent. So this term must be positive. So energy goes from thermal to kinetic. So the flux cannot decrease. Like here, the flux is decreasing, but in relevant convection, flux should increase. Okay, and we started. So this flux should increase with wave number. That's what we started to look for. We found that flux does not increase but remains flat, or approximately flat. Okay, and the flat, why it is so, is it has some subtle reasons which I cannot discuss because of lack of time, but the flux cannot decrease. So Buoyancy theory cannot work for Leonard. Okay, that is ruled out. Flux cannot decrease with for Leonard. Either it is increases or approximately flat. Okay, slight increase. Okay, the slight increase we can say. Okay? So that's the bottom line. And so all this Boolean wave number, that is not correct. That should not be the case. And the doubt, in fact, from a lot of experts, from Prokashya, Lvov, they extended the argument of Buoyancy to relevant convection, but that's not correct. Equations are the same, but this energy flux is not, behaves very differently. Okay. Now quickly we tried to simulate it. It turned out that there were not many simulations in the past. Try to verify Buoyancy. Okay, so we did this simulation, and it is not a very high result simulation. It is 1000 cube, and we found there is a 11 by 5. I multiply by 11 by 5 EK, and there is a flat region here. Okay, now okay, so this is not extremely conclusive, but we claim that okay, it is the case. So this flux, this is what uz theta. Okay, we uz theta. I put a minus sign, so uz theta is negative, so minus of uz theta is positive, and we indeed get this to be positive. So there are a lot of bits and pieces put together, and so we don't have strong evidence, but we have many weak evidences. So number of weak evidences and the argument. So the argument is very robust. The flux is negative, or I mean the energy transfer is negative, uz theta is negative for stability development. It's logical argument. That's what I would say. Now, Shadab, he is doing a PhD in our lab. He's did a shell model simulation. It turns out there is a region where 5/3 exists for, so there's a dual scaling. In fact, Buoyancy showed that there's a dual scaling. There's a 5/3 regime, and there's a 11 by 5 regime. So this part is 11 by 5 regime. There's 11 by 5 regime here. And then there's a 5/3 regime. Okay, so there's a 5/3 regime here. So both these things are not seen in our in simulations because we require a very, very high Reynolds number. And the Reynolds number in this work is around 10^5, but Richardson number is kept around 1. And we get this dual scaling with a lot of tuning. We get this. So there is a dual scaling. That's what we got in this paper. This is yet to be published. We're still writing it. Now, coming to Leonard, as I said, there are still papers which claim that it is Buoyancy, which is incorrect. So we did a pretty big simulation. In fact, this 4096 cube. So this later on it was done for that simulation, and this is kinetic energy spectrum EU multiplied by K 5/3, and this flat for more than a decade. Okay, and this is flat. More conclusive is this FUK. This is uz theta. Energy supply from thermal to potential is positive, and this is the thing. This term is negative for stably stratified turbulence, but it's positive for Rayleigh-Bénard, and that makes all the difference. Okay, flux tends to be flat. Okay, now the reason is, let me just make one small comment that though energy is supplied by plumes at all levels, but predominantly it is at large scales. Okay, it turns out it is surprising that small plumes are not really contributing to the dynamics as much as large plumes. And large plumes supply energy at large scales, and that is essentially like Kolmogorov forcing at large scales. Though there exists forcing at all scales, but it is more dominant at large scales. Okay, so these are the things about Buoyancy theory. It works only for stability stratified turbulence, not for Rayleigh-Bénard. Okay, Rayleigh-Bénard, it is Kolmogorov. That's what we find for many simulations, including small Prandtl number, moderate Prandtl number, large Prandtl number. The story is different. Large Prandtl number tends to be dissipative. Then there is a steeper spectrum. So large Prandtl number, these things won't work. But for moderate and small, this works very well. Okay. Now, very quickly, I will just make a reference to another work on rotating turbulence. Okay, decaying rotating turbulence. So here again, there are lots of spectrum, right? I mean, there's 5/3, there is -3, -2, and so on, so on. So we looked at only one parameter regime. This was work done by Manohar Sharma. So we did it for very fast rotation. So Rossby number is pretty tiny. So Rossby number is UL by omega. So it is very fast rotating turbulence. So this term is a Coriolis force. And what do we get? So we get this cyclonic flows, dominant cyclonic flow. There's anticyclone sitting here, but essentially, I mean, this cyclone is dominant in this. Okay. Now, what is the spectrum for this? For very small Rossby numbers. Now we find surprising. I mean, this was numerical work, but we are very confident about this. It was really, verified by lots of runs and so on. We found that the spectrum is very steep. The spectrum is falling down. This is for different times. This is the final time around 150 AD turnover time. Okay, and the spectrum for instrophy is like that. So for energy will be k -3 exponential. This part is exponential. This part is exponential minus k by kd squared. Okay. Now this looks pretty odd. I mean, what is this minus k squared spectrum coming from? Now this can be explained by slightly complicated argument. So flow is essentially 2D, is quasi 2D because of this tall vortex columns. Okay, but it's not quite Taylor columns, but it's nonlinear Taylor columns, if you may call. And the flux for instrophy. Okay, so the omega is 2D instrophy. So flux for instrophy decreases with your number by pure dissipation. Okay, and it turns out this is a flux which is positive. Instrophy flux is positive, but it is decreasing rapidly because this viscous term is pretty strong. Okay, this term is strong, and from this and some again set of assumptions and arguments, we can prove this one. So we use this idea of flux to determine the spectrum for stability stratified turbulence. It was not our work, but of course, Buoyancy told this many years back. But then we extended it to Rayleigh-Bénard convection, and we proved that it is not Buoyancy, it is Kolmogorov. And we also applied it to rotating turbulence. So my time is almost up. So I think I will conclude. And this is the conclusion slide. I only kind of did not provide a lot of details, but just like stating the results. So for stability stratified turbulence, Buoyancy scaling minus 11.5. This works only for Richardson number order 1. If Richardson number is large, then it won't work because it becomes quasi 2D. It's more complicated. Rayleigh-Bénard convection, it is minus 5/3. Flux is positive for this. And for rotating turbulence is complicated. Of course, we looked at only one regime, and we showed that the spectrum and flux are essentially exponential, and that is what is the thing. Power law is not there. I mean, power law is not there because there is a strong. Taylor columns, they contain a lot of energy, and the remaining ones are very poor, and they're essentially exponential. Okay, so with this, I will end.
Thank you, Professor Verma. If there is one quick question, we can take it. We're already out of time.
Maybe I can ask a question?
Yes.
If you can hear.
Yeah.
Okay,
Yes.
thank you. I have a question about direction of energy transfer. So usually the energy is transferred from larger energy levels to low energy levels. So it's a direct cascade. Or
Yes.
there can be inverse cascade.
Yes.
And you have also areas in spectra where it's almost flat. Does it mean that there is no any energy transfer from one scales to the other scales? And
No. Okay, please go on.
Yeah. And also sometimes in stratified fluid, if we have external forcing over a certain frequency, there can be energy pumping to other scales. External frequency will give more energy to other scales. I saw sometimes this in simulation. So is it possible to make a conclusion from the spectra or by some analysis, what is the direction of the energy transfer?
Okay.
Maybe I'm sorry if and thank you very much for the very interesting talk.
Okay, thank you. So the last one, the reference is my book. It is done in many places, but in my book I try to detail how to compute these fluxes. Okay, it's a compilation of lots of work. Here I'm sorry if I kind of did not explain it properly, but spectrum is minus 5/3. Often people multiply this by 5/3 so that it becomes flat. So EK K 5/3. This is flat. Okay, but spectrum, that means spectrum is K minus 5/3 for relevant convection. This one is 11/5. So spectrum is not flat. Okay, please keep in mind spectrum is 5/3 for this regime. So these are conclusions. Now for both, in fact, all these three cases, we find well, for these two cases the fluxes are kinetic energy flux is positive. For rotating turbulence, kinetic energy flux is negative for a very tiny regime, but instability flux is positive. Okay, which leads through the spectrum. So fluxes it's easy to compute now. I mean, I will not be able to tell you right now, but it is a standard thing which can be done. Now, coming to another question which you said about forcing. For stability, well, this is, we don't need any forcing. Here we don't force it. Thermal plumes force it all the time. Here we force only the large scales. Okay, we wanted to supply like a Buoyancy thing, we only force the large scale, but buoyancy is forcing at all scales. Rho G is forcing these two cases at all scales. Okay, so we do not control Rho G. Rho G is acting at all scales. We did not study what happens if we force by some external thing at different wave numbers. We did not do that. Our objective was to verify Buoyancy or Kolmogorov. That was our objective, and that's what we wanted to test.
Thank you. We're already running to the next talk. So there is a break after this talk. So in case anyone wants, we can extend the discussion there. So thank you, Professor Verma, once again.